Okay, we are going to talk today about limiting reactants. You might wonder what in the world I'm talking about. Hopefully that will be clear shortly. Let's go back to our cheese sandwich example. You know that if we have 2 slices of bread, 1 cheese, we get 1 sandwich. How many sandwiches, however, could we make if we go in the cupboard and we see, wow, we have 24 slices of bread, and I pull out of the refrigerator 18 slices of cheese? How many sandwiches could I make? It's a very easy example, but it's to illustrate a point. If I have 24 bread slices, I'll multiply that by my ratio 1 sandwich to 2 bread for every 2 pieces of bread. I can then make 12 sandwiches. That's how many sandwiches are possible. How many sandwiches are possible with the amount of cheese that I have? Well, I have a 1-to-1 ratio right there, so I can make 18 sandwiches. That's the total possible I could make with cheese. Clearly, I am limited by my bread, right? The answer is that can I make 12 or 18 sandwiches? I can only make 12. I couldn't possibly make 18 because I would run out of bread before I could use all the cheese. So, just to restate that, I run out of one before I can use all the other. In chemistry terms, the bread would be called the limiting reactant. It's the compound that runs out first, and it restricts the amount of product that could be created. The cheese is present in excess. If you'll notice, some of the problems we've been working on say we have this particular reactant in excess, or there is plenty of this, there is more than enough, it's in excess. It does not run out or limit the amount of product. In fact, there's some left over when the reaction is done. So let's apply this to an actual chemical example. Let's look at a process called the Haber process. It's a reaction used in the industrial production of ammonia. And here it is right here. We have nitrogen gas and hydrogen gas producing ammonia gas. So in our problem, we have 6 moles of nitrogen and 8 moles of hydrogen. How many moles of ammonia can be produced given those numbers? So remember, this is like our sandwich problem. One of these 2 reactants, either nitrogen or hydrogen, is going to run out first and limit our production of ammonia. Which one is it? So, use dimensional analysis to figure out which one it is. Find the number of moles of each one of these that can be produced and see which one is limiting our reaction. Well, hopefully you had a chance to try that. And here is the answer. If we have 6 moles of nitrogen, 8 moles of hydrogen, how many moles of ammonia can be produced? We're going to use the mole-to-mole ratios to predict how much product could be created from each reactant. So we have 6 moles of nitrogen that we start with. Here's our mole-to-mole ratio, 2 moles of ammonia produced for every 1 mole of nitrogen used. That gives us 12 moles of ammonia possible with this much nitrogen. What about with this much hydrogen? We have a 2-to-3 ratio of ammonia to hydrogen, and when we calculate that, we can make 5.3 moles of ammonia with this much hydrogen. So, since there is less ammonia produced in this second option, the hydrogen is our limiting reactant. We only get this much. It will run out first. What if we are not given the number of moles in the problem? What if we are given the number of grams of each of the reactants? For example, we have 125 grams of nitrogen gas, and this isn't quite color-coded, but 250 grams of hydrogen. How much ammonia can be produced in this case? Well, in this problem, we're going to first have to convert both of the reactants into moles. Then we can find out how many moles of ammonia each of those can produce, and we'll be able to see what our limiting reactant is. So first, let's find out the limiting reactant for each of those. Then, after we find the limiting reactant, if you kind of look ahead a little bit, we can convert our answer into grams and find out actually how much ammonia can be produced. So let's start by converting the reactants to moles. We have nitrogen, 125 grams, multiply by the molar mass, 28.02 grams per 1 mole. We get, I'll go ahead and cross these out. Those cancel. And right now we are at moles of nitrogen. We go ahead and convert that using the mole-to-mole ratio into the number of moles of ammonia that can be produced. 2 moles of ammonia to 1 mole of nitrogen. That gives us 8.92 moles of nitrogen that can be produced if we are relying on the amount of nitrogen we have. What if we're relying on the amount of hydrogen? How much could be produced there? Well, we multiply by the molar mass. Once again, the grams cancel from the top and the bottom. And then we multiply by our mole-to-mole ratio between hydrogen and nitrogen. Moles of hydrogen an ammonia, not nitrogen, excuse me. The moles of hydrogen cancel out. We're left with moles of ammonia. And the answer when we calculate it is 82.7 moles of ammonia that can be produced from our hydrogen. So which one's our limiting reactant? Nitrogen is our limiting reactant because it is going to run out first. It doesn't produce very much. So we can produce 8.92 moles of ammonia using the nitrogen. But remember, we typically don't leave our answer in moles because if I'm standing in a lab and I'd like to know how much of this I'm going to use, I would rather not have it in moles. So we go ahead and convert from moles back into grams by the using the molar mass. 1 mole of ammonia for 17.034 grams of NH3. That gives us this many grams of ammonia, and we are limited by, if we look back in all of these, 3 sig figs. So I'm going to have to round that to 152 grams of ammonia. And that would be my answer to how much ammonia can be produced. Now you try it. Aluminum reacts with chlorine gas to form aluminum chloride according to this equation. It's already balanced for you, so you don't have to worry. Let's say I have 10.0 grams of aluminum, and I react that with 35.0 grams of chlorine gas. What mass of aluminum chloride can be produced? And just in case you don't have a periodic table handy, this is no excuse. You can still do this problem. Here is the atomic mass for aluminum and for chlorine in case you don't have your periodic table. So go ahead and pause and see if you can work this problem out. So let's take a look at the answer. If we are given the amounts of each of these reactants, we'd like to know which one is going to limit so that we can find out the mass of aluminum chloride that actually is produced, right? We don't know which one's going to be limiting, so we're going to have to figure that out. We know that we have 10.0 grams of aluminum, and we know we have 35.0 grams of chlorine gas. So we can start with those, convert them to moles, multiply by the mole-to-mole ratio to find out the moles of aluminum chloride that is going to be produced by each of those. 10 grams of aluminum multiplied by the molar mass, and then the mole-to-mole ratio gives us 0.371 moles of aluminum chloride. If I look at my chlorine, I start with 35 grams multiplied by its molar mass and the mole-to-mole ratio with aluminum chloride, I get 0.329 moles of aluminum chloride. So which one is the limiting reactant? Down here, chlorine. It's the limiting reactant. It will run out first. Because chlorine is the limiting reactant, we can then use it to determine how much aluminum chloride we're actually going to have. Not in moles, but in grams. It's a little bit more useful. So let's take 0.329 moles of aluminum chloride that we produced with our chlorine, multiply by the molar mass for aluminum chloride, and we get 43.9 grams of aluminum chloride, correct number of sig figs, and that's how much we would get because of our limiting reactant of chlorine. There is another way that you can look at this approach. I'm not going to discuss it here, but in our next section, I'm going to look at another idea, and that's percent yield or theoretical yield. and I will introduce another way to think about how to look at limiting reactants. If this way makes sense to you, just stick with this and don't worry about how I am going about the calculation in the next video. But if you like the other approach, it's just a different way to look at it and a different way to go about calculating. So I look forward to seeing you in class and working on some more of these problems.